Thank you, because I'm not recording, but I'm recording now. Actually, maybe I should wait. There's still some people coming in. My little fans that keep my computer from heating up. They're really annoying though. If you touch the back of them, you feel like your finger's going to come off. It's not working too well today. Okay. All right. All right. So I just want to write this down that there is no class on Wednesday, and there is no lab this week. So, yeah. And, you know, if you have questions about the test or anything else, just email me. Okay. And I'll try to, you know, I can't do your quiz exam questions for you, but I could maybe push you in the right direction. Have you used that index that I gave you? Does anybody use that? I wouldn't mind knowing if you give me a thumbs up if you used it. I don't know. I see a few chats. That's good. Good. A couple of thumbs ups. All right. Okay. It's better than nothing. All right. Well, that's good. All right. So I also sent in my section of lab, I sent out emails today to people who are, you know, haven't handed in all the lab reports. So I haven't graded that many, but I am working on it. I'm going to grade another one tomorrow. So I'll probably have 4 of them graded for the midterm grades, which are due on Wednesday. So I'm going to have to come up with some kind of, you know, way of computing the grades based on the first exam and the graded assignments. I graded all 4 of them that I got. If you handed in graded assignment 4, you got it back, at least if you did it as of last night. You could still hand it in today. I put a little extension on that because it was a typo in the problem, but most people ignored it as well as me when I did it, but it is incorrect. So I thought I would use that as an excuse to give people another day to hand that in. And I will say that, you know, some of you didn't do so well on those, and you really should look at what I have to say on those, because there's questions on the exam that asks kind of similar things to some of them. So, you know, you could use what I say as, you know, to help you answer those questions. I'm going to post the solutions to graded assignment 4, like tomorrow morning. I'm just going to wait until midnight tonight to get whoever hasn't handed that in. That's, you know, those graded assignments are 10% of the grade. So you really should hand them in. Don't just not hand them in. It's not so good. So, all right. So as I said, we are in the equilibrium topic. And I also said this is extremely important. And actually, this topic is going to be with us for the rest of the semester, all through the acids unit. And even when we do thermo, we talk about equilibrium constants in there as well. So what I started to talk about last time was how reactions don't necessarily go to completion. And most of the time they end up in a state of equilibrium. That means they get to some point where the forward reaction and the backward reaction are both happening, and they're happening at equal rates. So we have basically reactants and products. And at some point, the rates of the forward and the reverse reactions become equal. Now, for some reactions, this is at the beginning where you've only made a little bit of products. At some reactions, you're almost to the products. Some reactions, it's really more in the middle, okay? And at that point, when the rates of going forward and going back become equal, what happens is that the concentration, so at equilibrium, the concentrations no longer change. Not only that, that's one thing, but that there is a quantity, this ratio of the concentrations of the products over the concentrations of the reactants, each raised to this stoichiometric power, right? So if we had, for example, 1A plus 2B goes to 3C, for example, that ratio, which we call KC or KEQ, we use the C is for when we're using concentration units or when we're using molarity. So this would be the concentration of C cubed over the concentration of A to the 1, because that's the stoichiometric value, and B squared, because so each is raised to their stoichiometric power. So not only do these concentrations not change anymore at equilibrium, but this ratio, this funny ratio, okay, of the concentrations of products over reactants, each raised to their stoichiometric value power, this reaches a certain, this has a certain value once equilibrium is reached. So once the reaction reaches equilibrium. And it doesn't change anymore after that. And the only thing that'll change that value of K is the temperature, but we don't get up to that for a while. Next time we'll get up to that. So I'm going to give you some additional info on the equilibrium constant, on Kc. So, oh, and when we have, yes, when we use concentration units, like these are molarities, these brackets, that's what it means, we use Kc. Later on, I'm going to show you Kp, where we use the partial pressures. We do that for gas phase reactions. But anyway, so here's some more information on the equilibrium constant. Okay, so if we have this reaction, 2 hydrogen molecules plus a carbon monoxide molecule goes to methanol in the gas phase. Okay, CH3OH. And we, just for practice, I'm going to write Kc for reaction 1. So it would be the concentration of CH3OH, notice there's a 1 there, so it'd be raised to the 1 power over the concentration of H2 squared, because it's the 2 there, and the concentration of CO to the 1. So I could just erase those 1s. They're just, they don't need to be there. So this is the value of the equilibrium constant. It would be whatever these concentrations are, concentrations at equilibrium. That's what these arrows are pointing to, right? Those concentrations have to be at equilibrium. That gives you the value of Kc for that reaction number 1. Now, if we had reaction number 2, and what's different about this reaction is it's just in the reverse direction. So it's basically the backward reaction of the first reaction. And you'll notice if you write the Kc for reaction 2, it's flipped. It has the hydrogen squared and the CO to the 1 on top, and it has the CH3OH to the 1 on the bottom. So how is this equilibrium constant related to this one? It's just a reciprocal. Okay, that's just 1 over Kc for reaction 1. So when you flip an equation, the equilibrium constant is the reciprocal of what the equilibrium constant was before you flipped it. So reversing an equation, the Kc is the reciprocal. It's 1 over whatever the K was going in one direction. And now I'm going to tell you that when you have a gas phase reaction like that, very often you don't talk about concentrations. When you have a reaction in the gas phase, what's probably going to be more convenient is to use the pressures, the partial pressures of each of the substances. So we have a related equilibrium constant, which we call a pressure equilibrium constant. And we call it Kp. And for the same reaction as the first one, okay, we would take, instead of the concentration of the product, we would take the partial pressure. That's the PCH3OH, that's the partial pressure of the methanol. So you basically have a flask, you know, and you have these 3 different gases in it. 3 different, okay, and you'll have a partial pressure of each one. So the partial pressure of CH3OH over the partial pressure of H2 squared, right? You still have to keep that power there of the stoichiometric coefficient, and the pressure of CO to the 1 as well. So this is called Kp. Now, Kp is not equal to Kc, right? Kc is with the concentrations. Because what is a concentration of anything? It's the moles per liter. All right. Well, moles per liter isn't the same as atmospheres. These have to be in atmosphere units. Don't do this with few exceptions. They have to be atmospheres. And so Kc is not equal to Kp. And there are a lot of books out there that spend a lot of time relating Kc to Kp. And it involves the ideal gas law. But, you know, I think that's really kind of stupid. I mean, you're either going to do the problem with pressures and atmospheres, and you're going to use Kp, or you're going to do the problem with molarities and use Kc. So I don't see any reason why we should be going back and forth between Kc and Kp. We will not do this. You are not responsible for that. So basically what you need to know is that, there's one more thing I wanted to tell you. Let's see. You don't need to know how to relate Kc to Kp, but I want to make a couple of comments about the units of the equilibrium constants. And, you know, basically, you never see a unit on a K. Well, why not? I mean, you have pressure here and you have pressure to the cubed in the bottom, right? So you'd think there would be an overall unit. They don't cancel. We never worry about units in equilibrium constants. There's a very good reason for that, but the reason is really beyond the scope of general chemistry, right? It has to do with how these are defined. And when you're using concentrations, it's actually that each of those concentrations is divided by a standard concentration of 1 molar. So the units actually cancel. But that's beyond us. For us, for our purposes, I would say you want to always use concentrations in molarity units. Okay, whether it's Kc, the equilibrium constant, or if you're doing a reaction quotient. Does anybody remember the difference between a Q and a K? What's the difference between a QC? What is a QC? Anybody? Boy, I'd be really impressed if somebody would know the answer to this. Nobody want to try? Did I miss a chat? Let me see if there's a chat. I don't see any chats. Well, QC is the same ratio, but not necessarily, let's just say, but not at equilibrium. Okay, that's the difference between the Q and the K. So when you're doing problems involving concentrations, you always use molarity units and you're all set. If you start changing to different units, then it doesn't work so well. Always use pressures in atmospheres when you're doing a problem with KP. Okay, whether it's a K or a Q. And don't put units on them. Don't worry about that, and you'll be fine. So keep your concentrations in molarity, keep your pressures in atmospheres, and all will be well. Okay. I don't know why I thought of that. What I just thought of, this weekend I discovered that I read the Los Angeles Times because my son lives out there. So I always want to know what's going on in LA. So they did this article, this all will be well reminded me of this, because there's a guy who lives in California somewhere who has been making literally a cartoon, like a New Yorker cartoon, except that they're colored and they're all different topics. And he has written one of these cartoons for every day of the pandemic for 365 days. And I was thinking one of them was about how all will be well, but I read 100 of them in one night. So I really thought they were very funny. Anyway, his name is Gary Handman. You can look him up on Instagram. And if you like his humor, then that's my sense of humor. So, and he's older like me, so you probably wouldn't get his jokes. No, you would. Anyway, I feel very silly. But, all right, so I'm going to tell you another very important thing. And this is regarding writing equilibrium constant expressions, those products over reactants to their stoichiometric power. So I'm going to show you by example. I think that's easier than talking about it without an example. So here is if you have lead iodide solid. Now, and you put it in water. And to tell you the truth, not much of this happens, because what this is showing is a solid becoming aqueous. So that is a process known as dissolving. And lead iodide is really pretty insoluble. So this only goes forward a little and mostly stays lead iodide, okay? So what happens is you put a certain amount of lead iodide in the flask, okay? And say you have 100 milliliters of water, and very quickly you get a whole lot of lead iodide sitting on the bottom and only a tiny amount of these guys, of the dissolved Pb2 plus and I minus. Okay, and we know that when that happens and we have solid down here and we've mixed and mixed and mixed, that this is a saturated solution. Okay, now a saturated solution is one that is at equilibrium. That means there's just as much solid dissolving. So the rate of that forward process is precisely the same as the rate of the aqueous ions coming together and forming the solid again. So that's an equilibrium situation. So this is an equilibrium. In fact, that's really the first equilibrium that we learned about in this class when I was talking about solubility. Okay. So it's a very small number of grams of lead iodide. What the hell happened there? Per milliliter of per 100 milliliters of water. It didn't share. What the heck is going on here, huh? Okay. Anyway, so if you're going to write the K for this process, okay, it's a Kc, all right, because it wouldn't make sense to give partial pressures of things that are aqueous. It would be the concentration of lead ions times the concentration of iodide ions squared. And then you might think that you would put the concentration of lead iodide solid in the denominator, but that is not what you do. So I'm going to cross that out. We never put solids or liquids. We never put pure solids or liquids. This is a pure solid in a Kc expression. All that matters is that there is a teeny tiny bit present. It doesn't matter what the concentration is. When you think about what is a concentration for a solid, okay, so a concentration is moles of the solid per liter of the solid, right? Moles per liter of the solid. Well, if you took and multiplied this by the molar mass, grams per mole, this turns into grams per liter. This is actually density. And what I'm saying is that the concentration of a pure solid or a pure liquid, I'm not talking about a solution, a pure solid or a pure liquid is constant. And so we simply leave it out of the K expression because it's not changing and we don't have to worry about it. So it's not changing and we don't need to worry about it. So never, so the end of it is never put a solid or a liquid. I'm not talking about solution. The solution is not a liquid, right? It's a solid or a liquid dissolved in another liquid. Never put a pure solid or a pure liquid in a Kc or a Qc expression. Okay, we leave them out. All right, so we would say that for that reaction, what you have, the products here, these are aqueous. They go in they'll be in the K, but not this one. So if you see a phase that's S or L, leave it out. If it's AQ or gas, then you put it in. All right. Never put a pure solid or in Kc. So Kc for the above reaction would simply be the lead ion times the iodide ion squared. So we just get rid of the denominator and we have just the numerator. So this Kc is the value of the concentration of lead times the concentration of I minus squared at equilibrium. Okay, so I'm going to go over some very basic skills that we use in this unit. One of them is writing expressions. So we're going to write the expressions for Kc and Kp. You know, I didn't have a chance to email this to you, but this is on Blackboard, right? This is activity 1 of unit 5. So if you have access to a printer, you can print this one, activity 1. You might want to print the first 5 of them. But like I said, they're on Blackboard under unit 5. Okay. So how would you write these expressions? Write the Kc and Kp. So Kc, oh, actually, I was going to do an example first. You know, I ran out of space. That's why I thought I was going to do that, but I actually have another example for you first. Okay, let me do that first. So take calcium carbonate and write the Kc and Kp expressions for this reaction. I'm illustrating a point here. Okay. So Kc, I'm going to leave out the pure solids. Look at that. I don't take either of those pure solids will not end up in the Kc expression. So I'll just have concentration of CO2. That's it. if I'm doing a pressure equilibrium constant, it would be the partial pressure of CO2. And that's it. Okay. So if I know the equilibrium concentration of CO2, so the concentration of CO2 at equilibrium is Kc. And here the partial pressure in atmospheres, this is in molarity, partial pressure in atmospheres of CO2 at equilibrium is Kp. So pure solids do not appear. Okay, so now I'm going to do this activity with you. So what would Kc be for this reaction? If you want to type it in the chat, that's a good idea. Go for it. And Kp. So these are our products. Products go on top. So we have concentration of H2O. What else? Concentration of CO2. And we don't have any stoichiometry. That's interesting here. This is a solid, doesn't appear. This is a solid, doesn't appear. So that's it. That's all there is. That's all she wrote. Kp would be the partial pressure of water times the partial pressure of CO2. So as long as there is some of each of these present, it absolutely doesn't matter how much. Okay. And of course, these have to be at equilibrium. I'm probably going to stop saying that at some point, but I want to drill it in that, you know, it's not a K. It's not going to be constant unless the reaction is at equilibrium. So that's really the simplest, you know, kind of problem you can have. So now it's talking about the same reaction. So I'm just going to write that reaction down again. Okay. So it tells you if the concentration of water and CO2 at equilibrium are both 0.00192. So how could this happen? You know, if I have a flask, stoppered flask, and I put in some sodium bicarbonate, that's what this is, that white solid, that's baking soda basically, and I just leave it with the stopper closed, okay, and I wait. A little bit later, I don't know how fast this reaction is, but you'll have a little bit less of that, okay? You'll have some of this solid, so you'll have some other solid in there, okay? And you'll also have two gases. You'll have H2O and CO2, okay? You'll have the same amount of these two, right? Because they each have a coefficient of 1, and however much of this reacts is going to produce the same amount of either one of these. All right, that's just to give you a little, you know, set the scene a little bit, you know. So it'll be forming a solid and it'll also be forming these two gases. So we know that at equilibrium, the product of these two concentrations is a constant, and we know that they're 0.00192 each, because these are the concentrations at equilibrium. And because we don't have to worry about units, I'm just going to leave the units off. So really all I have to do is plug in the same value for each of these, multiply them together, and I get 3.69 times 10 to the negative 6th is the value of the equilibrium constant for this reaction. And the solids never enter into it. They just have to be there. So now, suppose, now that you know what the K is, and you have a different flask, where you have a different concentration of water. What is the concentration of the CO2? So Kc is a product of those two. We know it's at equilibrium, an equilibrium mixture. So if we want to find out the concentration of CO2, we just divide both sides by the concentration of water. And we know the K value from up here, 3.69 times 10 to the negative 6th. And the concentration of water is 0.00250. So this comes out to 1.42 times 10 to the negative 3 molar is the concentration of CO2. Notice that these are not the same. The concentration of H2O is this. The concentration of CO2 is this. Well, what that means is this couldn't have started by just putting solid sodium bicarbonate in there. Because if that had been the case, then the water and the CO2 would be the same amount. This flask must have started out with at least some water vapor in there to begin with, to have the water be so much higher concentration. Well, actually, it's just a little higher. It's somewhat higher than this one. So because these are not equal, you shouldn't be scratching your head about that. They're produced in equal amounts, but you might have started with some water vapor, which is why they're not equal anymore. They're not equal in this case. So there's all kinds of different combinations that can happen. You can approach this equilibrium from all reactants or from all products or from having few of the things present, and then it comes to an equilibrium. Okay, so, all right. So very important information about equilibrium. So I would like to talk a little bit about what the values tell you. What do the values of the Ks tell you? So, so what do the values of Kc and Kp indicate? And I'm really talking about the magnitudes. Of course, all Ks are positive, but what does the size of the K tell you? So I first want to say that there is an absolutely huge, huge variation in values of Kc and Kp for different reactions. So that means, some Ks can be 10 to the negative 20th, be 10 to the 25th. There's just this ridiculously enormous variation. This is 45 orders of magnitude or powers of 10. So what does it mean for K to be a large number or a small number? Okay, well, don't forget that this ratio, Kc, for example, right, that's the products, concentration of products to this power. And it's the, however many products you have, you would have one of these factors for each one over the concentration of reactants to the stoichiometric power. Okay, it's basically products over reactants. Okay, it's not, depends on the stoichiometry, but I call it a ratio of products over reactants. Okay, so in general, if the value of Kc, and this is also true for Kp, is larger, what can you say about whether that reaction favors the products or favors the reactants? If the value of Kc is larger, which is favored? Which is favored more? Which would be larger, the numerator or the denominator, if the number is big? What's the answer to that question? More products. Yes, exactly. Thank you. Okay, so If the value of Kc is larger, it means products are favored. If Kp, if Kc or Kp is much greater than 1, so greater than 1, much greater than 1, then the products are heavily favored. And what that means is you have very large concentrations of the products and very small concentrations of the reactants. Because remember, the K is products over reactants. Bigger this is, the bigger the K is going to be. The smaller this is, the bigger the K is going to be. So if you have a value of Kc or Kp that's much greater than 1, products are heavily favored. You could have numbers, for example, like 10 to the 5th or 10 to the 7th or 10 to the 20th for Kp. You could also have 10 to the 2, not as heavily favored, right? So here the products are not as heavily favored. Here they're very heavily favored. Even here. Okay. All right. And of course, I could say exactly the opposite, which I'm taking for a lot more space than I thought to say, but that's all right. If Kc, Kp is much less than 1, then the opposite is true. Then reactants are heavily favored. Okay, that means the reaction really didn't go forward very much before it got to equilibrium. Okay, and you could have values like we'll see when we do the acids unit. Ka is for acid, 10 to the minus 3, 10 to the minus 7th. You could even have, you know, for other types of reactions, 10 to the minus 10th and things like that. These are very small values of K. There would be almost no products. And then if you have Kc or Kp that's like, you know, close to 1, like if it's equal to 5 or 2 or 0.2 or 10, these numbers are not very, very huge, much greater than 1. They're not really much smaller than 1. They're sort of medium values. And in cases like this, even like, you know, even if K is up to it's like 50 or something like that, you would have pretty significant amounts of both. Of course, it does also depend on the stoichiometry. So there would be significant amounts of both in an equilibrium mixture, which simply means in the reaction mixture at equilibrium. Okay, lots of both present. Okay, so so I'm going to go. Last time I went over. Let's see. And Kc is only a measure of equilibrium, not at any point in time. Yes, absolutely, that is correct. If it's not at equilibrium, we don't call it K, we call it Q, the reaction quotient. All right, so the K is only when we have a reaction mixture at equilibrium. Okay, so last time, the very last thing I did was what I call a type 2 problem. I gave you out a sheet and it's posted. Well, I didn't give out a sheet. You know what I mean? I posted a thing that talks about a type 2 problem and what a type 2 problem is. So I basically categorize these problems as 5 different types. And it's convenient so that you can always look them up and see, well, what is, you know, if I say it's a type 4 problem, what's being asked for, what's being given. So a type 1 problem basically had to do with if you know what the values at equilibrium are, you could find the K. Or if you know all but one and you have the K, you could find the others. Type 2 is a little bit different. It's a level up in difficulty. It's if you're given the initial concentrations of everything and one of the concentrations at equilibrium. So I tell you what everything is at the beginning. Starts out with a concentration of blah, blah, and blah. And at equilibrium, we know that the concentration of N2 in this problem is 1.14 molar. With that information, you can find the other concentrations and you can calculate the K. So that is a type 2 problem. You start with the initial concentrations of all the players in the reaction. That's the reactants and the products. You're given the concentration of one at equilibrium, and you calculate concentrations of all at equilibrium. And once you have that, you get the K. If you're given pressures, you'll get a Kp. If you're given molarity, you'll get a Kc. All right. Now, this problem, what I give you, so I'm not really giving you the concentrations directly, because what it says here is you start with 6 moles of N2 and 6 moles of H2 in a 4-liter flask. You know, the only reason I'm doing this is because Sapling does this all over the place. I think it's silly. I think it's stupid. I would have just said, well, I would have given you that it was 1.50 molar of each, because if you take 6 moles and 4 liters, that's 1.50 molar. But I just wanted to show you, because Sapling does this all the time. It gives you the moles and it gives you the liters, and you have to divide the moles by the liters to get the molarity. Okay, so you've seen it here first. So the answer to this is 1.50 molar. Now it says, if at equilibrium, the concentration of N2 is 1.14 molar, what are the concentrations of everything else at equilibrium? So I'm going to show you how to do this problem. This is, like I said, a type 2 problem. And I'm going to start by writing the reaction N2 with the stoichiometry plus 3H2 goes to 2NH3. I'm not going to put the phases here, even though they're all gas, because it's really not relevant in this problem. I'll make an ice chart. And an ice chart, the I means initial. The C means change. And the E means at equilibrium. So we just figured out, because it says that you have 6 moles of N2 and 6 moles of H2 in a 4-liter flask. So each of these concentrations is 1.50 molar. Now it does not mention NH3. Well, if it doesn't mention it, then it's not there. Okay, don't go making up that it's going to be such and such. It's not there, it's 0. Okay, so now, so the first thing you might want to think about is, which way is this reaction going to go? So what do you say about that? And this is something that's true most of the time. If you have a 0 for any product, it's got to go to the right. Because what is your QC here? QC is the concentration of NH3 squared over the concentration of N2 times the concentration of H2 cubed. And this is 0 over stuff. Well, it doesn't matter what these are. If this is 0, then this ratio is 0. I mean to write Q, is 0. And when QC is less than K, right? Well, it doesn't matter what K is. K could be 10 to the negative 20th. 0 is going to be less than that number. So the reaction goes forward. We don't know what K is here, but it doesn't matter. If you have nothing for a product, the reaction is going to go forward. If you have nothing for a reaction, the reaction is going to go backward. Okay, you're going to have something at equilibrium, even if it's very small. So it's going to go forward. All right. So now this is one of these cases where I do this let X equal business. Let X equal, okay? And immediately, the first thing you'll do with let X equal is you'll look for something that has a 1 as a stoichiometric coefficient. And that's the thing you're going to let X equal. You're going to let X equal the concentration of N2 that reacts. That means that negative X is the concentration, is the change in the concentration of N, is the change in the concentration of N2. Okay, because it's going away. It's a product. It's reacting away. So it's going to have a negative change. What the amount of N2 later is going to be less than the amount at the beginning. So the change will be negative. So whenever you have a reaction going forward, you'll have a negative in front of these X or whatever, 3X or whatever it turns out to be for the reactant. So the concentration, the negative X is the change in concentration of the N2. So if nitrogen changes by an amount minus X, what will hydrogen change by? You notice you have a stoichiometric coefficient here of 3. Is hydrogen going to change by the same amount as nitrogen?
No.
It's going to be 3X. Somebody said it, and it's not going to change. You're right, by the same amount as nitrogen. So do I put 3X in here?
Would it be negative 3X?
Got to be negative 3X because it's also a reactant. And now when it comes to here, what is going to be the change in the NH3 concentration? It's got a 2 there. So however much N2 reacted away, it's going to be twice that because you're producing NH3 2 for every 1 N2 that reacts. All right, so that's what we put in the change. And then what we do is we add this together.
Why is that one positive?
Because it's a product.
Okay.
And it's forming. So while nitrogen is going away and hydrogen is going away, their changes are negative because they're disappearing. They're getting less than what they started with. Ammonia started at nothing. And so it's going to end up with something. It's going to be positive. It's going to create ammonia, this reaction. So then what you do down here is you simply add these together. Now, since you have, when you have a negative, that's a subtraction. So this is at equilibrium, the concentration will be what it started with plus the change, which is negative. So it's 1.5 minus X. This is going to be the concentration of N2 at equilibrium. This will be 1.50 minus 3X. Because for every nitrogen that forms, you have 3 hydrogens that form, okay? So it's going to react away much more quickly. What about this one? Well, you start at 0 and you end up at 2X, so you're going to have 2X. So now, you know, it doesn't look like we're really any closer to solving this problem, but we really are. We are much closer to solving this problem. Why? Because we are also given another fact. If you go up here, this fact is the additional fact that you're given, that at equilibrium, the nitrogen concentration, the concentration of N2 is 1.14 molar. So how can I figure out what X is? I just take, this is the equilibrium concentration of nitrogen. The equilibrium concentration of N2 in terms of X is 1.50 minus X, and that's equal to 1.14 because that was given. So that allows me to solve for x. Now what I'm going to do is add x to both sides. And subtract 1.14 from both sides. 1.5 minus 1.14 is 0.36. Once I have x, my job is essentially done because I know what the concentration, this is the concentration of H2 at equilibrium. This is the concentration of NH3 at equilibrium in terms of x. So now I could say, okay, at equilibrium, the concentration of H2 is 1.50 minus 3x. So that's 1.50 minus 3 times 0.36. Okay. So I can do that. That's 1.50 minus, that's 0.42 molar. So that's the concentration of H2 at equilibrium. All right. I also know that the concentration of NH3 at equilibrium is equal to 2x. So 2 times 0.36, because x is 0.36, is 0.72. So that is the concentration of NH3 at equilibrium is 0.72 molar. Okay. So that's how I'm going to get everything. I set up my problem in terms of this x. In a type 2 problem, you're given one of the concentrations and you use that to solve for x. Once you have x, you plug it in to the different equations, that different expressions that you got, 1.5 minus 3x, 2x, and that's how you figure out the concentration of everything. Okay, so finally, the last thing you have to do in a problem like this is to find the value of K. But that's pretty easy to do once you know the concentrations of everything. So if you want to write the Kc expression, we had N2 plus 3H2 goes to 2NH3. So Kc is the concentration of NH3 squared over N2 to the 1 and H2 cubed. So plugging all these numbers in, I have 0.72 squared over 1.14, that's the one that was given, and then 0.42 for the H2. And if you do the math there, and you only have 2 sig figs here, because you only have 2 in these 2 numbers, it comes out to 6.1, which is the value of K. That's your second type 2 problem. I did one last time. You should have another look at that now that you've seen another one. I'd actually, let's see what time it is, 3 o'clock, good. I am going to show you another type 2 problem, but I'd like you to work on this one because I think you need to actually practice this yourselves. So here is a type 2 problem. This is activity 3. I'm going to just keep it up here. I'm going to give you 5 minutes to set this up. I want you to at least set it up. Okay. Oh, and you can follow these directions. Okay. This is pressures, okay? So you're actually going to be finding a KP. So you'll start by writing in the value of the initial pressure, fill in all the initial pressures. Then you have to figure out the change in pressures of reactants and products in terms of an X. Notice you have coefficients of 1 here. So this is an easier example than the other one. So I'm just going to give you 5 minutes. You can ask me questions if you want to. Okay. I'll just put in these initial. These are pressures in atmospheres. How's everybody doing? Okay, so what am I going to put in this box here?
Negative x.
That's right, because it's got a coefficient of 1. And then what goes in the next box?
Negative x.
That's right. Good. And what about this box?
Two.
Sorry. Say again.
2x.
That's right, because HI is being produced 2 for every one H2 that goes away, and for every one I2 that goes away. So now we just add this up. Just add what's in initial plus the change. Basically, we just, here it's a subtraction. Here it's 0 plus 2x. Okay. And now we look for the other information, which says the reaction below occurs, and at equilibrium, the pressure of HI is 4.39. That's the important part. So that means that I know that at equilibrium, this is 4.39. So the reason that's great is because it allows me to solve for x. Okay. Did anybody do that?
Yeah.
And what'd you get?
2.195 or 2.2.
Around 2.20, but that's fine. Good. So that is not the answer to any question, actually, except for what is x. Now we have to say, well, 2x, right? The concentration of HI is 2x. So that's 2 times 2.20 atmospheres. So that's 4.40 atmospheres. Okay, we also know that the concentration of H2 is 12.3 minus x, so that's 12.3 minus 2.20. If you do the math there, you get 10.1 as the concentration. Actually, these aren't concentrations, I'm wrong. They're really pressures. Okay, sorry about that. Okay, 10.1 atmospheres. H2, we have, so now we have HI and we have H2, and now we have, this is the iodine, Pi2 is 2.56 minus x, which is 0.365, only 2 decimal places. I just keep an extra one because it's a 5 and I underline to show the sig figs. Okay, did anybody get as far as finding the Kp? Probably not. That would be if you look at the reaction, it would be PHI squared over PH2 PI2. So it'd be, this is the HI, 4.40 over 10.1, 0.365. And that comes out to 5.2. And that is the answer. So that's also a type 2 problem. Okay. So I'm going to go on to a different type of problem. Actually, this is activity 4A and 4B. So this is a type 5 problem. And type 5, I explained last time, is that there's an easy part. Did someone get 1.21 for the K? Was I wrong? No, I think mine's right. Anyway, so the easy part of a type 5 problem is, which way will the reaction go? To do that, you have to find the Q and compare it to the K. But then there's another part. So that's what the A part is. The B part is, what will the concentrations be at equilibrium? And we can't do this yet. But we can figure out which way this reaction is going to go. So place solid, this particular solid. I'm so bad at art. Why can I be so bad? Negative flask. So I place this solid, which is NH4HS, in a flask, and it also has some ammonia in it. 0.50 atmospheres of NH3. So I've got some ammonia in it. It says, which way will the reaction go? All right, so now when you have a solid here and you're solving an equilibrium problem, only thing that matters is you have some there. It does not matter what the concentration is. It never appears in the equilibrium constant, so we just put a line. We're not worrying about that. The H2S is not mentioned. Therefore, it is 0. Okay, don't go thinking it's the same as the NH3. If it doesn't say it is, then it's not. The ammonia concentration is 0.50 atmospheres. So that is your initial situation. All right. Now, what we're trying to figure out is which way will this reaction go? So you have to figure out the Q. And here it'll be a QP. So this is, remember, the same ratio as the K, except what it actually is at some point in time, not at equilibrium. So this is 0, right? This is the pressure of H2S times the pressure of NH3. So it's 0 times 0.50, which is 0. The K is 0.11, but it doesn't matter what the K is. Since the Q is 0, the reaction's got to go forward. And we talked about this last class. When QP is less than KP, the reaction goes forward. Okay, and that's the case here. So that's the answer to that question. The reaction goes forward. The second part we can't do yet. That actually is a type 4 problem. And I'm going to show you that next. Well, after I do one other example. So 4A you can do. You could say the reaction goes forward because the Q is 0. And of course, that's going to be less than the K. Now I'm going to talk about activity 5A and 5B. Very similar situation. So 5A, figure out the direction of the reaction given the initial concentrations. So here's a reaction, and we're told that initially we have 1 molar of everything. Actually, it's 1 molar, yes. All right. So how do we figure out which way this reaction is going to go? We figure out what QC is. That's the reaction quotient. That's the pressure of H2 times the pressure of Br2 over the pressure of HBr squared, because you have a 2 here, at any point in the reaction. And at this point, everything is 1. So it's 1 times 1 over 1 squared. Well, 1 squared is 1. So this is 1. I made some easy numbers. So QC is 1. What's the K? K is 1.6 times 10 to the minus 2. So this is greater than the KP, which is 1.6 times 10 to the negative 2, or 0.016. So since QP is greater than Kp, which way is this reaction going to go? So you can think about it this way. When Q is greater than K, the products are too big to make that number come down. The products are going to have to go down and the reactants are going to have to go up. So the reaction will go in reverse. You can reason it out, or you can just remember when QP is greater than KP, the reaction goes in reverse. So that's the answer to that. To figure out what are the equilibrium concentrations, that's harder. And that involves what we call a type 4 problem, which I'm going to tell you how to solve next. Okay, so I have an example of a type 4 problem. And I'm going to do it now. Let's see, where is it? Oh, that's all right. It's actually from this handout. Let me see if I can pull it up. I talked about this handout last class. It's the one that has the activities, the different types of activities on it, different types of problems, I should say. And I'm going to copy. Okay, so this is, it's a hypothetical, you know, Z2 is like a diatomic molecule going to 2Z. It's like H2 going to 2H or something like that. So a type 4 problem is when you are given the K. So we tell you the equilibrium constant and we give you the initial concentrations and you're asked to find the final concentrations. Now for this problem, the K was given earlier and the Kc was 5. So this is given. So you're given the equilibrium constant, you're given the initial concentrations, and you have to find all the equilibrium concentrations. So when you know how to do this type of problem, you'll be able to go back and do problem 4b and 5b, because remember I said those are type 4 problems. Okay, this is also activity 6, by the way. It's the same problem. So how are you going to solve this? You're going to set up an ice chart. So I'm going to start from the beginning because I'll have it all written better than that typed stuff. Okay, so here's your hypothetical reaction. And it says initially that you have 0.4 molar of each of these. Okay. So the first thing you might want to ask is, which way is this reaction going to go? Okay. And for that, you need the Q. So that's 0.4 squared over 0.4, right? So we have this concentration squared over this concentration because it doesn't have a power. So that's just going to be 0.4. And since the K is 5, QC is less than KC. So the reaction goes forward, which, okay, that's good. So what do I put here in this change? What is the change in the concentration of Z2 if this reaction goes forward? What would I put in that box? So it really starts just like a type 2 problem. So what do I put in here? Since you have a 1, what am I going to let X equal? You know, what do I put in this box?
Negative X.
Negative X, exactly. And the next box?
0.4 for the 2Z, because on top it said 0.
Oh, that's right. I was wondering why I never explored which way this reaction would go. It's because I didn't have to, because it was 0. So all that is baloney. Thank you for pointing that out before I got too far into this problem. So which way? It'll go forward. And that's because there are 0 products. I'm sorry about that. So you could cross that other stuff out. If it was 0.4, that's how you would do it, but it's not. Thank you. Who said that? That was great. So what is this going to be in this red box here?
2x.
2x, exactly. And here I'm going to put 0.4 minus x. So it's basically adding these up. And this is just going to be 0 plus 2x or 2x. So this is where the type of problem diverges from a type 2 problem. In a type 2 problem, you're given what one of these concentrations is, and it allows you to figure out x that way. But in a type 4 problem, you have to get it another way, and it's a harder way. Okay, so what you have to do at this point is you have to set up the Kc or Kp expression. So we know that here we're dealing with concentration. So it's Kc is the concentration of Z squared over the concentration of Z2. So in terms of x, so you have to put this in terms of x. Well, Z is 2x, so that's 2x squared over 0.4 minus x. And that is equal to the equilibrium constant, which I told you is given as 5. And this is the equation that has to be solved for x. You must solve this for x. But you're going to have a little help, okay? So the first thing you have to do is you have to manipulate this equation, which what I would do is I would cross multiply. I would say this times, multiply those two equals those two. So I'll have 2x squared times 1, so I'm not going to write that, equals 0.4 minus x times 5. Okay. Now, I'm just going to tell you, what is 2x squared? What is this equal to in terms of x? Just put it in the chat. Or somebody say it. What is 2x squared? Is it 2x squared? It's 4x squared. Yeah, it's not 2x squared. But a lot of people in the class would put 2x squared there, and it would make the whole problem wrong. 2x squared is 2x times 2x, which is 4x squared. So don't forget to put a parentheses around it, and don't forget to square the whole thing. And don't forget, it's 2 times 2 times x times x. It's 4x squared. And now you're going to have to do this. You're going to have to distribute this 5. Okay, so you'll have 0.4 times 5 minus x times 5. Okay, and 0.4 times 5 is 2. And this is 5x. Okay. Now I keep the sig figs. You have to, what you might want to do is just keep in your mind how many sig figs you have, because I know most of you are not going to write 0.400. But then if you give me your answer to 1 sig fig, I'm going to take off points. So please, if you see 3 sig figs here, it's probably going to end up being 3 sig figs. So try to keep track of the sig figs. So now, I don't know if you remember way back in high school that you learned the quadratic form of an equation. So I'm going to put this, you could see I have an x squared here. So this is a quadratic equation. And I'm going to put it in quadratic form. And quadratic form is ax squared plus bx plus c equals 0, where a and b and c are constants. So that means I'm going to keep my 4x squared on the left, and I'm going to move everything else over to the left. So I have my 4x squared is 2 minus 5x. I am going to add 5x to both sides. I'll get 4x squared plus 5x equals 2. But now I'm going to subtract 2 from both sides and get 0. So I'll have 4x squared plus 5x minus 2 equals 0. And you could see that I have 4, 5.00, and 2.0, negative 2, right? This is my C, this is my B, and this is my A. Now, does anybody know how to solve this equation? How do you solve an equation flow? So what is X? Anybody know? Anybody ever heard of the quadratic formula? Yes, good.
Yes.
You
Well,
know what it is? Minus B,
minus b,
plus or minus.
the square root of 2,
Now, don't give me the numbers in terms of A, B, and C. Minus 4.
a, 4a.
Right, this is a quadratic formula. And this is how what you have to use to solve it. Except remember I said you're going to get a little help. Okay, I don't need for you to be doing this. Okay, so I'm going to show you where you can go online to get a quadratic solver. There are lots of them, but I'm going to show you one of them. All right, so all you need to know is that A is 4, B is 5, C is negative 2. So don't forget that negative sign there because it makes a big difference. So let's see. Oh, this computer is driving me nuts. So sick of this thing. I'd like to take it back. All right. So I'm going to share my screen and go over here. I want to show you how to get this site. So I go to Google, right? And I type in math.com quadratic. Oops, quadratic solver. Okay. And I go there and I get this nice thing here. All right. And I can type in for A 4. It's really 4.00. But let me tell you, the quadratic solver doesn't care about sig figs. Make this higher up so you can see that. So I might as well doesn't matter if I put in 4.00 or if I put in 4. So I just put in 4. B is 5. And C is negative 2. Because those are my A, B, and C that I got. And then you just hit this little gray thing that says solve. Okay. Now, as you probably remember, or hopefully remember from high school, when you solve a quadratic equation, you get 2 solutions. We call them 2 roots of the equation. And you'll notice here that one is 0.3187 and one is negative 1.57. So I have those numbers written down. So I'm going to go back into OneNote and share my screen again. Let's see. Hold on. What a pain in the neck. All right. Okay, so you go to the math.com quadratic solver. And you end up getting the solution. So this is what it looks like, right? This is what we had. Filled in these boxes, 4, 5, 2, -2. And then you solve it and you get two numbers here. I just took the liberty of only giving you a few sig figs, 3 sig figs. And these were the two solutions. They're the two x's. A quadratic will always give you two solutions, usually. Which one of these do I pick? Well, remember, these are the values of x. We want the value of x. If we go back and look at how the problem was set up, we know that the reaction goes forward. And we know that x is therefore positive in this particular problem. That may not be true in every single problem, but it's true in most of them. X is positive. So that means that I'm not going to pick the -1. I will pick the positive x. This is not always going to work, although it works in most problems. It works when you I don't want to get into that right now. But anyway, so you pick the positive x because you know x is positive, okay? So generally what happens is one of the solutions is right and the other one is impossible. It just doesn't make any sense. It would mean a negative molarity or something like that, okay? So what we know is that x is the 0.319. So we also know, if you go back and you look at when we set up this problem, the concentration of Z is 2x at equilibrium, and the concentration of Z2, the concentration of Z2 is 0.4 minus x. So let me write that down before I forget it. The concentration of Z2 is 0.4 minus x. The concentration of Z is 2x. This is at equilibrium from our setup. So the concentration of Z2 is 0.4 minus 0.319, which is 0.081. So that's molar. The concentration of Z is 2 times 0.319, which is 0.636 molar. Now, you can do what I call a check. This check doesn't find every single mistake, but it finds a mistake if you set up the problem right, but you didn't manage to solve this right. It'll tell you. So the way you do a check is you know that the Kc should be 5. So that means that the concentration of the, so remember the reaction was Z2 goes to 2Z, is that right? Yeah. So Kc would be the concentration of Z squared over the concentration of Z2, and that's 0.636 squared over 0.081. And if you calculate that, it comes out to 4.99, which is supposed to be 5. So that is, baby, close enough. Okay, so you go check. Okay, and of course, if you set the problem up wrong, that's still not going to be right. But if you set it up right, that is a great way of checking. Okay, so that is the basic, that is a type 4 problem. That's the most difficult type that you would have to solve. But I'm going to show you something else. I'm going to show you another example. This is activity 7. And it's a type 4 problem, but you don't always need to solve a quadratic. So let me show you this situation where this happens. And this is very similar. This is similar to, I put up the sapling homework for equilibrium. Sapling unit 5, number 10 is like this problem. Okay, so it's actually the I2 plus H2 goes to 2HI reaction. And at some temperature, the equilibrium constant changes with temperature. So it can give you any value of an equilibrium constant. It gives all students different values. But it takes care of that by saying at some temperature, the equilibrium constant is 53.3. So it'll give someone else at some temperature, the equilibrium constant is 25.3, and it goes all through it. So anyway, it gives you the initial concentrations are 3 molar of the two reactants and 0 for the products. So if you set up your ice chart, you would put minus X here. You know the reaction is going to go forward because you have no product. And this is going to be 2X. So you have 3 minus X, 3 minus X, and 2X here. So Kc, which is 53.3, is equal to 2X squared over 0.3 minus X times 0.3 minus X. So if you look at this closely, you see that you have 53.3 equals 2X squared over, now this is the same thing. So this is 0.3 minus X squared. So this is actually 2X over 0.3 minus X, whole thing squared. So what you can do when you have that is you could take the square root of both sides. I meant to do that in red, but it didn't happen. What is the square root of this? This thing is all squared. So it's just 2X over 0.3 minus X equals the square root of 53.3, which is 7.30. And this is not a quadratic. So this is easier to solve. But this only works when you have these reactants start at the same concentration and they have the same stoichiometric coefficient. If they started at different concentrations, then they wouldn't be the same here, and this wouldn't work. So it works in certain special cases, but it's much easier to solve because now when you do your cross multiplication and you end up with an equation, so 2X equals 7.30 times 0.3 minus X, you see that there's no X squared anywhere. 2X equals, this is 2.19 minus 7.30. So you still have to distribute, but now you can just move all the X's onto one side. So you'll have 9.30X equals 2.19. And X is 2.1. And so you don't have to use a quadratic solver. So that is 0.235 molar. So now you know that the iodine concentration, which is the same as the H2 concentration, is 0.3 minus X, 0.3 minus 0.235. And what if I had solved this problem and I had X is 0.6 and I have iodine equals H2 is 0.3 minus 0.6, comes out negative. Well, that doesn't make any sense. So maybe I didn't set the problem up right. So you have to look at that. You have to think about this. So this comes out to 0.065 molar. That's what the concentrations of these guys are. And the concentration of HI, which is 2X, which is 2 times this 0.235, or 0.470 molar. Okay, And then you could check the answer as well here, because the K is the HI concentration squared over H2 I2 0.470 squared over 0.065 times 0.065. And that comes out to 52.2, which is close enough to the 53. What was it? 53 point. It's close enough. Round off error. Don't worry too much about it. These problems are hard enough without having to deal with that too much. I'm going to tell you this, even though I know you're working on the test and you're not going to do this for a while, but activity 8 is going to be graded assignment 5. Okay. And I'm probably going to have it due about a week from today. And it is a type 4 problem. And 5B, these activities, we did 5A today and we did 4A today. 5B and 4B, they're also type 4 problems. And these will be special problems, extra credit. And I'm going to post this online, but I know that they'll be due, say, Monday. So the test is due Thursday. If you can't make it to hand it in Thursday, you need to send me an email, okay? And, do that if you can't make it. Don't just not hand it in. That's just not a good strategy. You need to tell your teacher, okay? So we're actually, this is a fast unit. We're going to finish it on Monday and start acids. So, we're going to be heavily into equilibrium for a while, but we're going to call it something else. We're going to call it acids. It's a fast unit. So anyway, do the exam, and then, work on these over the weekend. And if you need my help, you need to email me and I will meet you on Zoom. Okay. All right. That's all I have for today. If you have questions, you can stay after class. Otherwise, goodbye. Have a great day, everybody.
Have a fun, Professor. Bye.
Bye.
Professor.
Yeah.
So I worked all weekend, so I wasn't able to make any of them. I just had a couple questions. I didn't know if you wanted me to do it another time or if now is fine.
Why don't we wait for most of the people to clear out and then we'll do it, if that's all right with you.
Oh, yeah.
If you want to come back in 20 minutes, that's okay too. Yeah. Either way. How many people are left in here? Let's see. There's only 12. Maybe other people have questions too, so I can still do it when other people are here. Are the other people who are here going to ask questions, or are you just not you haven't left yet because you're not at your desk or whatever? Because I think I'll just address the questions that Ashley has, and if anyone else wants to listen, that's fine. So why don't you just go ahead and ask me those questions?
So for question 3 on mine, it was talking about the lattice enthalpy.
Which is your quiz?
2, version B.
And which question?
For 3, I guess it's A and B. I know how to explain it, but I just don't know how to write the chemical equation. Through my notes, I can see why like, for example, if it's like large and positive or something like that, but I don't know how to figure out the equation.
Well, what's the index page? What did I tell you to, did you have that in front of you? Question? Which day of notes was that?
Wednesday, February 24th.
It's after this. Maybe it's part B. No, it would be before this.
Yeah, I said A, sorry.
Yeah, that's all right. All right, so we use NaCl as a model, right?
Yes.
So this is the chemical equation for the lattice that has a delta H that's equal to the lattice enthalpy for, what is the problem? I'm just gonna do a Control-Alt-Delete and then get it back again, because this is never a good sign when it says that.
So if it's CS and CL, I'm basically putting that in.
Yeah, I mean, it's almost exactly the same as that. It's just the metal that's different, right?
Yeah, the CS and the, yes.
So I think that's your answer right there. I'm gonna go and share it again, but. Wait a minute. Sorry.
No, I think I was just overthinking it. Like, I didn't know if I did
Thinking it because it's, yeah. So
the literal
let me
equation.
go. What's February 24th? Okay. Yeah, so the equation is here for sodium chloride, and yours is cesium chloride. This is the equation 1 here is the equation that's got a delta H, that's the lattice enthalpy. And the second equation is the one for that has a delta H equal to the hydration enthalpy. Is that it? So do you understand why this is large and positive, and why this is large and negative?
Well, because you have to break the ionic bonds and they're super strong for.
Yeah, and you're really not getting anything back, because when these go into the gas phase, they don't interact at all. So,
Okay, yeah, I was definitely overthinking that one then.
I think so.
Okay, so then for 5, it's about like the delta T and then the KB. I figured out the delta TB for A, but am I accounting for the fact that it's ionic? So am I using that little weird I?
You have to use the weird I, yes.
Okay. Okay. I think that's good. And then for 6, I figured out A, it's like it multiplied by 4 and then the rate was by 4, but for B, when you multiply it by 4, it increases by 4.
Wait.
Sorry.
I'm sorry. Let me, can you say that again?
For 6, for
I got 6, yeah.
for A, when you go from one to another, it's multiplied by 4, and then the rate
Why
is
don't you get a little, when you go to another, so you're doubling? What?
quadrupling, I would say.
Well, you always want the concentration to just double. Are you talking about what happens to the rate?
Yeah. I
So
mean,
you want to pick, because, can you say it again? Because what you said, I have to interpret it, and can you just say it again? Here it is. Can you see it?
yeah. Okay, so for A, for 0.01 to 0.04, that's multiplied by.
Why would you pick those two?
Well, I don't know.
Don't pick those two. Pick 2 where A changes by a factor of 2 and B changes not at all.
Okay, okay.
I'm sure you'll be able to find two that do that.
Yeah, okay, all right.
Okay.
I
Yeah, so I mean, it's harder to, I mean, you could do it. I guess you could do that. A quadrupling, did you find that it was by a factor of what? From 1 to 2?
I didn't get that far. Once I saw that, I'm like, well, this is just extra.
Let's pick. So what you should do is not pick those two. Just because they're the first doesn't mean you have to pick those.
Okay.
So
So I
find something else.
0.04 and 0.08, it goes up by 2.
Yeah,
Okay.
that might be a better one to pick. Okay.
Okay, I think I'm good there then.
Mm-hmm. Mm-hmm.
Okay, thank you.
You're welcome. Okay. Is anyone else? Jacob, you got a question? Hagerlin? Grace? Are you there? Well, I'm going to assume you're not there because you're not saying anything.